CGM and IGM, and we're going to start with a talk by Daisuke Nagai on cosmology and astrophysics with CGM in the stage 4 era.
Is it on? Let's see. Hello, can you hear me? Okay, great. For the past decade or so, my research has focused more on hot gas in massive galaxy clusters. But the research has been developing to the point that sort of looking ahead into the next era, especially in light of the Astro 2020 Decadal Survey, thinking more ambitiously about the future direction of that field for studying the diffuse gas in dark matter halos. One of the new exciting area that has been identified is to actually study these the circumgalactic medium, the gaseous medium that are filling the galactic size scale objects from low redshift all the way to high redshift. I would like to start with these figures. Over the last decade or so, there has been a significant progress in mapping out these hot intercluster medium out to the large radii in the virialized regions using Suzaku telescope, Chandra telescope, as well as the new technique that are emerging, which is called using the microwave telescope from Planck mission. The idea of this, the microwave telescope is to use this cosmic microwave background as a backlight. And when the low energy photons scatter off the hot electrons that are embedded within the galaxy clusters, you can actually study the distributions and properties of gas embedded in these massive galaxy clusters. So so by combining these X-ray and microwave technique, there has been quite a bit of a progress in understanding thermodynamic properties of gas embedded within massive cluster out to very large radii. I would like to think of this sort of the galaxy cluster as a test bed for the studies of the circumgalactic medium in the coming decade. There has been significant progress also on the smaller mass scale, especially through HST cost survey, through absorption studies. There has been a detection and characterization of the detailed properties of the CGM, the gas embedded within the smaller mass halos. But what I'd like to argue today is that in the future, this is one of the growing area where we can expect to actually see significant advances. For the purpose of this talk, I'm going to focus on this technique in microwave through the Sunyaev-Zoldovich effect, using CMB as a backlight and trying to actually map out the diffuse medium out to very large redshift. I should just remind that the Sunyaev-Zoldovich effect is the inverse Compton scattering of a CMB photon through the hot electrons and warm electron embedded within a halo. Nice thing about this effect is that this effect is independent of redshift. No matter where the clusters and galaxies are, as long as the hot diffuse medium exists, this absorption signature is imprinted in this cosmic microwave background, which is filling the entire sky. Using this technique, the thousands of clusters has been detected, and the counting of galaxy cluster, for example, has been used to actually derive things like cosmological parameter, which led to recent Planck CMB cluster tension. I will not go into the details of this tension that is actually facing our community, but suffice it to say that the key idea, the challenges that we're facing in thermal SZ effect science is to connect these observable SZ signal to the mass of the galaxy cluster, which is one of the major uncertainty and major problem even for the existing telescopes. At the same time, there's actually a new technique that is emerging through the kinematic SZ effect. These are much smaller effect compared to thermal SZ effect, and which measures the peculiar velocity, motions of the halo that are moving within space with respect to the CMB background. Detecting the KSZ effect on individual clusters is extremely challenging because the spectral signature of the KSZ effect is degenerate cosmic microwave background, which is much, much brighter. But the recent progress in this area actually took advantage of basically combining the CMB survey with galaxy survey, and by actually stacking the CMB pixel at the locations of the galaxies from the galaxy survey, you can actually construct the statistics that allows us to actually measure this pairwise velocity, the relative velocity of two halos. The technique actually takes advantage of the fact that the two halo that are close to each other in space are gravitationally attracting each other, so that there is a relative velocity of two halo that are nearby should be both attracting toward us. So if you were to measure radial velocity of these galaxies or pairwise velocity of these galaxies, you expect the negative signal. Velocity is going to left toward us or away from us, and when you correlate those two velocity, you should expect to see the negative KSZ signal, which has been detected in 2012 for the first time. So this is statistical measurements of the peculiar velocities of the halos for thousands of objects, or thousands of galaxies, and also clusters. You can take take any of the tracers as a galaxies or clusters from the optical surveys, and you can detect these peculiar velocity, pairwise peculiar velocities as a function of separation between two halo. So that's very exciting. The signal to noise of this measurement initially was of few, and there has been many measurements that has been made over the last few years. And in the future observation, the survey will expect to increase the signal to noise by a significant amount. So the problem here is that the signal that we're measuring is not just the pairwise velocity, which contains interesting information about cosmology, but also multiplied by the amount of electron that are embedded within the galaxies and clusters. So the amplitude is proportional to optical depth of electrons within the halo. So there's a significant astrophysics that goes into determining the total amount of electron embedded in the halo, and that's one of the key astrophysical uncertainty, and one of the major the problem that we're facing for this technique to be sort of used for cosmology is to really understand this so-called galaxy dark matter halo connection, analogous to the galaxy dark matter halo connections. In terms of, so once you actually measure those pairwise velocities from KSZ effect for a future survey, you can actually gain information about Hubble parameter, angular diameter distance, growth factor, but of course it's also degenerate with optical depth. The information potentially contains unique information, information about modified gravity. You can distinguish F of R gravity with DGP gravity, for example. So this kinematic SZ effect, measurements of velocity of a halo, in addition to counting of the halo that you will do with the thermal SZ effect, will provide actually new information. So that's potentially interesting. The main uncertainty, as I said, is the optical depth. If you have actually an external prior on optical depth of these galaxies and clusters to better than about 20%, you can marginalize over this, and this is the constraint that you expect to get. But if you can actually get the external prior, understanding of the optical depth in clusters and galaxies down to better than 20%, then the astrophysical uncertainty will no longer be an issue. We can actually go, this technique will be cosmology ready. So in terms of actually detecting the CGM, or the warm gas out to large radii, I think thermal and kinematic SZ effect is a potentially powerful probe of mapping out the gas down to about 10 to the 12 solar masses out to arbitrary large redshift where the halo actually exists. And it's quite complementary to X-ray technique, absorption line studies from UV, fast radio burst. So there's the SZ also occupies some of the unique parameter space, especially at high redshift, owing to the redshift independence of this effect. What's interesting in the future, so this is the plot from the CMB-S4 collaboration, which is actually from the AstroPH today, or actually earlier in March. The future CMB mission should be able to actually measure the electron optical depth as a function of radius. This is cumulative optical depth. This is cumulative thermal energy contained within the halo for the 10 to the 13 solar mass object at redshift of 0.2 and 1.0. This is a landscape of where we are in terms of predictions of the gas density and thermal pressure profile, or predicted by the variety of galaxy formation simulation from Bahama with varying amount of AGN feedback. If you actually have a lesser feedback, higher feedback, lower feedback, there's a significant dependence on the energy feedback on many of these properties. And in the future, so if you actually combine the expected CMB-S4 Simon Observatory measurements with actually the future galaxy survey out to high redshift, this is expected constraints on density and pressure profile, which can help distinguish the density and pressure profile predicted by modern galaxy formation simulation, which in turn will then tell us about the variety of subgrid feedback recipes that are being put in to these modern simulations. Okay. So that's sort of what's incoming. I think we can actually, over the next decade or so, we can expect to actually learn, using CMB experiment, the stacked CMB measurement, to actually learn something about possibly feedback or galaxy formation, especially through the CGM measurements. So, for time being, most of the information that we have about the gas embedded within the halo actually comes from the massive halo, where we see the gas out the very large radii. This is the research that we've been focusing on. This is a suite of so we've been doing a suite of simulations, zooming cosmological simulation of 500 megaparsec regions, and one of the main takeaway messages that we've learned, well, the cluster core physics continues to be quite complicated. Things like AGN feedback, thermal conduction, magnetic fields are all very important. The properties of the core in the central regions of cluster is not, it starts to actually look well behaved and matches observation, but it's not at the point where we can start to make prediction, well-defined predictions. But it turns out in the outskirts of galaxy cluster, the feedback is actually not particularly important. There, the physics is quite different. What's most important is the gas accretion that are actually in merger, that are actually fueling the outskirts of galaxy cluster and some of the non-equilibrium phenomena in the outskirts of clusters. For the purpose of this talk, I'll show you 3 examples of the three physical processes that are important, that will likely be important for SZ survey. And one of the key idea here is that we want to model the distribution of gas not as a function of mass alone, but also as a function of secondary parameters such as mass accretion rate, to model the diversity of halo and gaseous medium in the outskirts of clusters. So here's one example. Actually, in recent, sorry. So recently, in using our dark matter only simulation, there has been a discovery of this outer edge of the dark matter halo known as the splashback radius. We can ask the same question: what is the outer edge of the gaseous medium? It turns out that it's about a factor of 2 larger than the location of splashback radius, origin of which was actually not particularly well understood. If you take the secondary infall model that predicts the location of shock radius and gas radius, or the canonical model, you expect those two actually to be on the same location. Hydrosimulation predicts otherwise. However, and what's also important is the location of the shock radius and splashback radius does depend on this thing called mass accretion rate, gamma, which is the mass difference between redshift of 0 and redshift of 0.5. So the fast accreting object, or higher gamma, tends to have more momentum, and the location of splashback radius is slightly smaller compared to the slowly accreting object, which has much less angular much less momentum. Okay. Sorry about this. Okay. Seems like there's a technical issue here. There you go. Another quantity is that the shape of the dark matter halo. That too also depends on the mass accretion rate. So this is the larger axis versus the smallest axis for the X-ray isophotes. Plot is a function of mass accretion rate. That the shape of the gaseous medium in galaxy cluster also shows correlation with the accretion rate. The higher the accretion rate, the more elongated the gas shape is. Okay, thank you. Okay, and then the last but not least, the accretion process and merging process actually generate a significant amount of turbulence. And so here's the plot of the non-thermal pressure provided by the random and turbulent motion as a function of radius. The simulation predicts that the non-thermal pressure increases rapidly from the central regions to outskirts of clusters. In the central regions, the turbulent motion provides about 10%, which is a small fraction, which leads to the biases in hydrostatic equilibrium if you actually made that assumption to actually infer the mass of the galaxy clusters. But this non-thermal pressure increases very rapidly. It could be as much as 30–40% in the outskirts of clusters. Another important thing is that the level of turbulence do depend on the mass accretion history of the cluster. Slowly accreting object does not have as much of the non-thermal pressure support compared to highly accreting object, which are thought to be the dynamically active object where the recent injection of energy into turbulent motion, which has not yet dissipated into heat. Okay. So these are some of the insights that we've learned from Omega 500 suite hydro simulations, but the simulation is still too expensive for us to actually make a predictive quantitative predictions for the upcoming all-sky survey, including CMB and large-scale structures. So one of the efforts that we're trying to do is to learn from these the physical insights from the observation and put it into slightly more computationally but still physically motivated model of gas in ICM and CGM. The model assumes the gas is in hydrostatic equilibrium. We assume that the gas radiatively cools, so some of the gas actually turns into stars based on the stellar mass-halo mass relation. The recipe actually includes the energy feedback. It's a single parameter based on this, the feedback efficiency, which is the amount of energy that is coupled to the surrounding medium due to stars and black holes. This also includes the effect of non-thermal pressure that I talked about, which is radially dependent out to larger radii. So the more non-thermal pressure means that there is less thermal pressure, and therefore, for example, there will be less SZ effect. So all of that can actually be incorporated into a simple one-dimensional analytical model, which we have constructed and presented in Flender 2017. This is the illustrations of what happens when you change the feedback from 0 to some finite number, the fiducial parameter. It has effects on suppressing the amount of optical depth in the low mass regime, but not so much in high mass regime where the gravitational potential is significant. So the AGM feedback doesn't have very much effect at all on high mass, but then it does have effect on groups and galaxies. And we can also see that the amount of conversion rate of gas into stars has effect on optical depth as well. So this is what the model actually behaves when you change some of the key parameters. One thing we could do to test whether the model actually captures essential physics is to compare simulation with the varying input physics, non-radiative, meaning that you turn off all the galaxy formation physics, and you turn on the cooling star formation, add aging feedback on top, and that actually changes the optical depth as a function of mass, which is the key quantities that we need to measure for, we need to predict for KSZ effect. And indeed, when you tune the parameter of the analytical model appropriately in the regime that's for non-radiative to the feedback with AGN, you can reproduce the amplitude as well as the mass dependence of these effects that are captured in more expensive simulations. So another thing we can do, thank you, and is to actually take this analytical model, which consists of actually 8 parameters, and ask, okay, what do actually X-ray measurements, which has a very small error, but these are X-ray measurements from Chandra observation following up on SPT selected cluster sample, and ask, okay, how much constraint can we actually derive from the X-ray observation in the framework of this model. So we're looking at the density profile for the redshift range of 0 all the way up to redshift of 1.3, and as well as the gas mass fraction, gas as a function of mass, down to from the 10 to the 15 to 10 to the 13 solar masses in the local universe. So if you put these data sets from the Chandra archive, and you can actually you can constrain the parameter of this model, AGN feedback. The detail is not as particularly important, but we're doing MCMC change to kind of constrain the combination of these models. And the end result here is that the optical depth of galaxy clusters as a function of radius can be constrained to something like 4% at high mass n, and it's about something like 12% in the groups 5 times 10 to the 13 solar masses. So the X-ray observation, existing X-ray observation provided very tight constraints on optical depth, better than 20% that we need to actually do cosmology. So if we're interested in doing cosmology using KSZ effect, if we restrict ourselves down to 5 times 10 to the 13 solar masses, we can actually start doing cosmology. Of course, I have not much of the future statistical sample will come from, from the lower mass system with the CGM, and this is the area where we're expecting to see more future constraints. So I'm just going to stop here. Over the next few years, I think we're expecting we're actually getting into the golden age of clusters and galaxy cosmology. We're expecting something on the order of 100,000 to million clusters and galaxies. It's a huge statistical power. But we still need to, the challenges that we face is to understand how the gas relates to the halo and understand the astrophysical processes. Hydro simulations are a little too expensive to span the parameter space of astrophysics and cosmology and its degeneracy. So we're developing some computationally efficient model that capture some of the key essence that we're learning from modern hydrodynamic simulations. I'll stop here, and thank you very much.
Thank you. Can I ask the next speaker to go ahead and come on up? So following on yesterday, I would like to encourage questions from the younger half of the audience. So if you're a grad student or a postdoc or a junior faculty member, what questions do you have? Hold on, Neil, hold on. Anybody else? All right, you don't count. Okay, Neil. Yeah, so switch this. There you go.
All right, excellent.
Okay, so our next speaker will be Gabriele Pazzulli, talking about a high baryon fraction and gentle feedback in massive halos at redshift 3.
All right. So good morning, everyone. And this is actually my first time at the Santa Cruz Galaxy Workshop, and actually my first time in